to talk a little bit more about this equation. X to the power k is congruent to d modulo. When we restrict now to prime modulus, because I will be able to say much more when considering the prime modulus. So what happens here? Well, we know when k is relatively prime to d minus 1, which is phi of d. Then we know this equation has just one solution. What we still don't know is what happens if k is not relatively prime to d minus 1. How many solutions will we have? Well, we just showed that this equation has no more than k solutions. Basically, I want to show that, well, I want to actually count the number of solutions in this equation. And to do this, we'll have kind of long discussion, and in the end of this long discussion, we'll return back to this question. But this question is basically about what happens if you take a number and raise it, well, to some power. So maybe let's start with just some simple numeric example. What happens indeed when you just take a number and raise it to the power? So example, numerical example. X to the power k modulo t for different x and different k. So let me take p equal to 7 and see what happens if I take a number and keep raising to different powers. Well, 1 to any power is always congruent to 1. Modulo 7. If you take 2, well, you have kind of sequence of different powers. 2, then you have 2 squared, which is 4. So I get to here by taking 2 and multiplying it by 2. 2 cubed is 8, which is 1 modulo 7. And then I repeat this cycle. If I multiply 1 by 2, I will get 2. If I keep multiplying, I'll get 4, 1, 2, 4, 1. So 2, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and so on. So I keep moving along this cycle. Let me try different one. If I start with 3 and multiply it by 3, I get 3 squared, which is 9, which is 2. And multiply it by 2, by 3, I get 3 cubed. Well, it's 2 times 3, which is 6. Maybe it's easier to write minus 1. And multiply it by 3, I get negative 3. I multiply it by 3, I get negative 9, which is negative 2. I multiply negative 2 by 3, I get minus 6, which happens to be 1. I multiply it by 2, and I get, by 3, and I get back to the beginning of this cycle. And then I continue moving along this cycle. This is 3 squared, 3 cubed, and so on, 3 to the power 7, 3 to the power 8, and so on and so on. Okay, let's continue and see what other cycles do we get. If I start with 4, 4 squared is 16, which is 2. I multiply it by 4 once again, I get 8, which is 1. And now my cycle is closed. You see that this cycle is kind of the reverse of this cycle. Here I'm moving from 2 to 1 to 4. Sorry. Yes. From 2 to 1 to 4. Here I'm moving from 2 to 4 to 1. So it's kind of in the opposite way. Does anyone see a reason why these cycles are kind of the same but with arrows reversed? Yeah.
Is that cycle we're just going 2 steps on that cycle?
Okay, that's one of the explanations. Maybe kind of a little bit better is, well, because 2 and 4 are inverses of each other. One of them is always moving in one direction, but the other one just cancels it. So if you have here from 2 to 4 to 1, here you have from 1 to 4 to 2. So here you have indeed from 1, sorry, from 2 to 4 to 1. Yes, from 1 to 4 to 2, yes. Okay, so what will happen is 5. So one of the things I can do is actually compute it, but maybe it doesn't make sense to compute because I know what is the inverse of 5. What is the inverse of 5? Yes. So 3 times 5 is 15, which is 1 modulo 7. So 5 will just move me along the same cycle, but in the opposite direction. So let me do it like this. Times 5. Times 5. Okay, and finally, one final cycle, minus 1. Minus 1 squared is 1. So it's a very short cycle of length 2. So here we have a cycle of length 1, cycle of length 3, cycle of length 6, cycle of length 3, and cycle of length 2. So maybe a couple of questions. First question. Suppose we take any other prime p and we start doing this procedure. We take a raise it to a, keep raising it to some powers. We will always get a cycle. We will always get such a picture. Okay, so why yes?
Fermat's little theorem.
Okay, Fermat's little theorem. If you take any number and raise it to the power p minus 1, you'll get to 1. Okay, yes, indeed. So if you take any number, you move enough steps along, well, whatever you get in between, you'll get to number 1. You make one more step, and well, now you're back to the initial number. But maybe the picture will look somewhat like this. I mean, maybe you go somewhere, then you apply some step, then you come back to this one, and then you come back to the beginning. Is that possible? Well, kind of no obvious reason. Out of these numbers, there should be only one error point. I mean, you multiply that number, and you always get the same result. Unless you make a computational mistake. So, indeed, always you get a cycle. Maybe another explanation is, why is it a cycle? Well, in one direction you always get, or maybe that was a good explanation. Let me keep it like this. Okay, what about the length of this cycle? What are the possible lengths? It seems that here at least we get all possible divisors of 6. 1, 2, 3, and 6. And 6 is in this case p minus 1. So maybe let's start with showing that that's part of the general picture. You always get cycles of lengths which are dividing p minus 1. Let me first give a name to this thing, the length of the cycle. It's called order. Multiplicative order sometimes. So let me formulate a definition. T is prime and A is not 0 modulo P. Then find order of A modulo P to be the following number. It's the minimal number m such that A to the power m is congruent to 1 modulo P. So it's exactly the length of this cycle. The number of steps you should make until you get to 1 modulo P. And here's a very simple claim. If A to the power k is congruent to 1 modulo P, then let me formulate it like this. You can reach 1 by moving along the cycle if and only if K is divisible by this order. Well, in a sense, there is nothing to prove now. We already know that we have a cycle. What does it mean that we get to 1? Well, it means that we make an integer number of cycles. It means that the number of steps is divisible by the length of this cycle. Maybe if you're not convinced by a geometric picture, let me write an algebraic proof. Even though the geometric picture is rigorous enough, once you have an explanation for why you have in this process an actual cycle, well, now the explanation is rigorous enough. Let's still have an algebraic explanation. Yes? Okay, so this thing is called the order of A, the multiplicative order of A modulo B. It means, well, it is the smallest number, smallest exponent, to which you should raise, smallest power, to which you should raise A, to get 1 modulo B. So let me give you examples. Order of, say, -1 modulo 5 is equal to 2. So any other number P order of -1 modulo B is equal to 2, because -1 itself is not equal to 1, but -1 squared is already 1. Here the definition is -1 is not equal to 0 modulo 5. -1 squared is equal to 0 modulo 5. Order of, let's say, 2 modulo 5. Oh, here's 1. Yes, sorry. What is the order of 2 modulo 5? Well, just keep computing. 2 squared is -1, 2 cubed is -2, 2 to the 4th is 1. So it is 4. And the explanation is once again 2 to the power 1 is not congruent to 1, 2 to the power 2 is -1, which is not congruent to 1, 2 cubed is congruent to 3, which is not congruent to 1, 2 to the 4th is congruent to 1. smallest power to which I can raise this number a to get 1. Yeah.
So before you have to show that it's well defined, right? So you have to show that the minimum is
Okay. So we have a collection of natural numbers.
you have to show that it's cycle.
Well, so we have a collection of natural numbers. We know that it's not empty because, well, one of the explanations is Fermat-Little's theorem. Another explanation we have just a finite number of elements. And we have some kind of path in this finite set which should close on itself after some finite number of steps. So basically, any collection of natural numbers which is not empty, there is a minimum element.
So you have to show that it's also always.
Okay, yes, so the fact that the cycle closes on itself, so the fact that the picture looks not like this, but rather like this, well, it follows from the fact that a to the power p minus 1 is equal to 1. So after p minus 1 steps, we always get to the number 1, and in the next step, we'll just close the cycle. Maybe let's prove this claim without relying on Fermat-Little's theorem because it's actually simpler, much simpler. So once again, the claim is like this. If you happen to find some power of a to which you should raise a and get 1, then you know that the order divides this power. So for example, 2 to the power 8 is equal to 1 modulo 5. So maybe let me give you an example. 2 to the power 8 is equal to 1 modulo 5. 4, which is the order of 2 modulo 5, does divide 8. So just an example. If you compute 2 to the power 8, it happens to be 1. So one possible reason is because the minimal power to which you should raise 2 to get 1 modulo 5 is 4. So let me give you a proof of the claim. Well, in one direction. If k is a multiple of the order, so this direction, if k is m times order of a, then s to the power k is equal to s to the power order a times m, which you can rewrite as a to the power of the order raised to the power m. But by definition, a to the power of its order is congruent to 1. So that's by definition. So one implication is just obvious, the other one is maybe slightly less obvious, but still quite easy. In the other direction, if you know that a to the power k is 1, is congruent to 1 modulo p, if a to the power k is congruent to 1 modulo p, then you want to show that k is divisible by this number order. And is the order a modulo p. Well, I want to show that k is divisible by m. Let me write it as a multiple of m plus perhaps some remainder. Like k plus q times m plus some remainder, and this remainder being from 0 to m, yes. So, then the following holds. Then I can compute a to the power r. What is a to the power r? It is a to the power k minus qm. But look, it is a to the power k times a to the power m raised to the power q minus q. Raised to the power minus q. But a to the power k is equal to 1, and a to the power m is equal to 1. Just because m is the order. So this is congruent to 1 modulo p. But how is that possible? M is the minimal number to which you should raise a to get 1. But here you raise it to the power r. So since m is the minimal number, such that x to the power m is congruent to 1 modulo p follows r is equal to 0. E and 0 is 0. So once again, here the argument is like this. If you know that a to the power k is 1 and a to the power m is 1, you know that a to the power of basically any linear combination of k and m is also equal to 1. But you can make this linear combination equal to this remainder of division k by m. Well, because remainder is a number which is smaller than m, and you know that a to the power of this number is equal to 1, you can put this number as basically 0. It can't be any actual natural number. Okay, in particular, it follows that the order of a number is always the divisor of p minus 1. Why is that? Fermat's-Nichols theory. Yes. So corollary. Order of A modulo P always divides P minus 1. A to the power of 2 minus 1 is congruent to 1 modulo P. And from this and what we just proved, it follows that the order of A is the divisor of this number, P minus 1. So, next thing I want to discuss is, well, how many different numbers of a given order are there? So suppose I want to find all the numbers which have, I don't know, order 2. Well, I have 2 examples. Sorry, I have just one example. Minus 1. Minus 1 modulo A prime, which is not equal to 2, has order 2. Are there any other numbers? which have order 2. So, let me try to answer these questions. Not only the 2, for general questions, we decide. We'll make a series of observations, and in the end we'll get an extremely precise answer, just a complete answer. So, observation number 1. Number of solutions of this equation, x to the power k is constant to 1 modulo p, is at most k. So that's really, well, that's something that we proved in the first hour. You have a polynomial equation of degree k, not all of its coefficients are divisible by p. For example, this one is 1, that one is 1. So it has at most k different roots. Well, in terms of the orders of x, I can reformulate the same statement in the following way. Number of elements, residues, whose order divides k is at most k. That's the same statement. Indeed, we know that x to the power k is congruent to 1 modulo p if and only if the order of x divides k. We just proved it. So here's a statement, well, which gives you a kind of inequality about how many different numbers, how many different residues might have order, well, which is the divisor of k. I would be interested in actually knowing how many different residues other whose order is exactly equal to k. Well, let me make the following observation. So, there is one kind of funny option. It is possible that just no number has order equal to k. It is a possibility. So, let me assume that there is at least one residue whose order is equal to k. If A order A modulo p is equal to k. So suppose that there is such a number. Then I will count precisely how many numbers have order equal to k. So here's how I will do it. Then, first of all, I will be able to describe all solutions of this equation. And all solutions of x to the power k is congruent to 1 modulo p are 1, a squared up to a to the power k minus 1. Yes, k minus 1. So not only this equation has at most k solutions, it has exactly k solutions. Moreover, here are the solutions. Well, indeed, it is obvious that each one of these numbers is a solution. If you take each one of these numbers, a to some power, and you raise it to power k, well, indeed, I can take even this number 1 and write it as a to the power 0. So indeed, if you take a to the power from I and raise it to the power k, you get the same thing as you would get if you first raise it to power k and then raise the result to power I. but this a to the power k is 1 by assumption. Order of a is equal to k. So these numbers are indeed solutions. So a to the power I are solutions of x to the power k is congruent to 1 modulo a. So maybe it's a good thing to ask you, is it all I have to show? I mean, here I have a statement, did I already prove it? So here are, it seems that there are k solutions here. And I know that my equation has the smallest k solutions, hence these are exactly its solutions. Is that right? Yes, I didn't show they are different. It's possible that I just repeated the same solution here k times and then, well, what did I do? Maybe half of them are the same and the other half is different, or something like this. So they are different indeed. If a to the power I is congruent to a to the power j, then a to the power for I, which is, let me say that I is the small one of the two, and each one of them is between 0 and k. So suppose I take two different numbers, I'll take one of them called a to the power I, the other one a to the power j. Let me show that this is impossible if I is not the same as j. Well, then a to the power I minus j is congruent to 1 modulo p. But then I know that the order of a divides I minus j. Hence k, which is the order of a modulo p, divides the difference. But this difference is a positive number between 0 and k. So it means I minus j is positive and is smaller than k. Hence, I is equal to j. It's not possible for this number to be divisible with k.
In that case, do you want to switch the I and the j in the 0 plus mu to I as the
Oh,
j?
yes, I did want to choose the I to be the greater of j. Yes. Okay, so now we have indeed k different solutions to this equation, polynomial equation of degree k, so they are all the solutions. So now I prove this statement. All the solutions for this equation are exactly those. In particular, every element whose order is equal to k will be one of those. So if I want to find all possible numbers whose order is equal to k, I'll just have to take numbers of this kind and see when such a number has order equal to k. So if in particular, order of B is equal to k. We already said here finished in previous equation. And now returning back to the question of how many different numbers would have order equal to a fixed number k. So I want to count them. If order of B is equal to k, then B is a to some power I, some I between k and 0. Well, but of course, not every number of this form has order k. For example, if I is equal to 0, then this number is just 1, and its order is equal to 1. So among these numbers, among such numbers, only the numbers a to the power I with I which is relatively prime. Okay, have order k. That's what I claim. So, yes, if the order of some number is equal to k, then it is of such a form. But if I take a number of this form and I compute its order, I claim that it will be equal exactly to k only if I is actually relatively prime to k. Here is the proof. Well, what is order of a to the power I? By definition, it's the minimal number m such that a to the power I to the power, and I should say a natural number m, such that a to the power I to the power m is congruent to 1 modulo p. But if I know what is the order of A, then I know that this thing is equal to 1 modulo P if and only if the order of A divides I times m. So I can say that this is minimum natural number such that order of A divides I times m. It's just the same thing. So if you want this number to be equal exactly to this order, to this k, if you know that the minimal number m, say that once you multiply it by I, the minimal number m say that once you multiply it by I, the result is divisible by k. If you want this number to be actually equal to k, well, it means that this I doesn't have any factor in common with k. It means that I times m is divisible by k if and only if m is divisible by k. So order a to the power I is equal to k if and only if GCD of I and k is equal to 1. So once again, if there is some common factor, then you can multiply this number I by m divided by this common factor and get the result which is divisible by k. So this minimal number which will be smaller than k. And vice versa. If I doesn't have any common factor with k, then we multiply it by any number which is not divisible by k, we get a number which is still not divisible by k. Okay, so let me, in the last 2 minutes, formulate what we achieved. And we achieved quite a lot. So it's kind of theorem. It's not the final form of the theorem, but almost. If there is at least one number A with order A which is equal to k, then we can take any its power which is relatively prime to k. We'll get a number whose order is equal to k, and that's it. No more numbers whose order is equal to k. Then there are exactly 5 of k numbers, residues of order k, and they are here. A to the power I, is I, rho to the prime, k, and I is between 0 and k. So, example. So that's just a statement that we already proved. If there is at least one number whose order is k, then all the numbers whose order is equal to k are of this order. How many are there? Well, just the number of i's which are relatively prime to k. So this number is called 5k. Example, if I want to count the elements of order 3 modulo 7, well, what are they? This result tells me that they should get exactly 2 elements. So there are 5, 3, which is 2 such elements. And they are one of them is say 2 squared. 2 is not equal to 1, 2 squared is still not equal to 1, but 2, which is 8, is equal to 1. And the other one is, well, it should be 2 squared, which is 4. And if you compute 4 squared is not equal to 1, but 4 cubed, 64 is equal to 1. So 63 is divisible by 7. Maybe another example, if p is equal to 7, k is equal to 4, there are no elements of order 4. So we actually need this, that there is at least one number whose order is equal to the given k. So why there are no elements of order 4 modulo 7? Let's start the sentence. Because the order of any element divides p minus 1, yes. So it must divide 7 minus 1, which is 6. So order of an element modulo 7 should be 1, 2, 3, or 6, but it can never be 4. Okay, so next time we'll see that for any divisor of p minus 1, there is an element of order k.